All right. So last piece for chapter 2 is just to talk about acid-base chemistry in terms of organic. It's principally about the Bronsted-Lowry theory and the Lewis acid-base theory. Of course, at its most fundamental level, we're talking about common acid-base reactions being hydrogen ions being picked up by hydroxide ions to form water. And historically, that was the natural ideology behind an acid-base reaction, a reaction that produced water. Of course, today we know that's a way too simple a way of thinking about it. There are many acid-base reactions that don't produce water, and many don't even occur in the presence of water. The Bronsted-Lowry theory gives us a pretty good starting point. And there are certainly lots of acid-base reactions in organic chemistry that we can describe using the Bronsted-Lowry theory. Bronsted and Lowry tell us that an acid is a proton-donating chemical. So we look at how that chemical begins the reaction, and we look at what we've got left at the end of the reaction. It's now missing one or more of its hydrogen ions, one or more of its protons. So we get this idea that a Bronsted-Lowry acid is a proton donator. If there's a chemical giving protons away, there must be chemicals which are accepting, receiving those protons, and that's a Bronsted-Lowry base. And so the Bronsted-Lowry definition of an acid-base reaction is a proton transfer from the acid to the base. Everybody remember to get a copy of the lecture notes. Remember the lecture notes that you see in front of you, there's like a 98% version which is available on Desire to Learn. I wouldn't want people to be trying to write at 100 miles an hour the entire lecture. That's just no fun whatsoever. You might have to throw something at me to remind me where the gaps are, so I'm not talking when you're trying to write something down, because that would be annoying too. Keep in mind that most acid-base reactions are fully reversible. And so as we read the equation from right to left, we also have an acid-base reaction. Everything gets cracked in reverse. The chemical that gave away the proton, which we consider to be the conjugate partner of the acid, now has the role of picking that proton back up. Taking the action that we expect for a base. So over that reversible system, we see these conjugate pairs which only differ by the presence or absence of a proton. The chemical giving away the proton is the acid of the pair. The chemical picking up the proton is the base of the pair. Conjugate pairs are always made up of an acid and a base. And of course, one of these two reactions is probably favoured by the position of equilibrium, the stronger reaction. And so the chemical which is part of the unfavoured reaction, which we're suggesting here by the length of the equilibrium arrows. So going from left to right, that's swimming against a stream, so to speak, which is predominantly moving from right to left. You could also look at an equilibrium constant which could back this up. Swimming against the stream, so not only is it an acid, but it's also a relatively weak acid. Meanwhile, its conjugate partner, which is flowing with the favoured direction, part of the favoured reaction driving equilibrium to the left, we see that that is a strong base. We always see conjugate pairs in this way. One of them is good at their job and therefore considered strong. One of them is terrible at their job and therefore considered weak. So if we have a weak acid, it means we must have a strong conjugate base. Or if we have a strong acid, it has a weak conjugate base comparatively. One of them is an acid, one of them is a base, but only one of them can be good at their job because they're part of the two competing reactions in the equilibrium mixture. Let's take a look at another, it's kind of poking up.
So in that example, would the third term, where you say the conjugate base, is that the predominant one?
Let's see, so equilibrium is being driven to the left. So well, these chemicals, the acid and base, they're very good at transferring that proton. And so when you're good at something, you turn into your conjugate partner. Like if you're good at delivering the mail, then you don't have any of the mail at the end of the day. So if you still have stacks of mail in your possession, you must have done a lousy job at delivering mail. So the evidence of how good they are is how they are chemically changed into their conjugate partner. Because that's their job. That's a sign that they have indeed transferred that proton as they're supposed to. Meanwhile, with a high concentration of these chemicals at equilibrium, if he's still hanging on to the proton, he's not very good at giving protons away. Like you wouldn't consider someone to be very charitable if they don't donate much money to a charity. Likewise, water here at H2O, having had its conjugate give the proton away in order to turn into this, then its conjugate must have been good at its job. And if this is supposed to pick up protons in the forward reaction, if it still exists in this form, not very good at its job. In fact, you might even say it's rubbish. So the proof of the pudding is always, did it do the job it's supposed to, and therefore turn into its conjugate partner? And that's what we get out of the Bronsted-Lowry theory. The idea of this proton being transferred back and forth. Problem is that there are many acid-base reactions that don't involve the exchange of protons. You need to look at the Lewis acid-base theory. Let's try a quick couple of examples for us. Am I repeating myself? Have we already done this part? We did? Okay, I guess just as a little refresher. So we've done this one here, my brain's kicking in. So we did that one, we've seen that proton transfer from the acid to the base. So we produce ammonium ions and the nitrate. Talked about the pKa, taking the negative log of the acid constant. I think maybe we more truly, I think this is the last one we did, I think, wasn't it? Not correct? Mm-hmm. Yeah, okay. So remember drawing those resonance structures. Okay. So I think the one on the next page is the one we're on. Apologies, I was so preoccupied in the last hour trying to find that camera stand and just video this. So this is the one we're on, is that right?
Yeah.
Yeah. Right. Here's the last quick example. So looking to transfer that proton using water as the base again. Remember, water is amphiprotic. It can act as an acid or a base, pick up protons or give them away. We're looking at it as a base this time. So there's a proton that we're trying to get rid of. And it is an acidic proton. You've got this carbon to oxygen double bond. Because of the greater electronegativity of oxygen, that's a polar bond. But the polarization doesn't just stop there. If this pure carbon, feeling electron deficient, it starts to bully electrons away from its carbon neighbour, drawing the electrons in that bond towards it. And so this poor carbon and the bond to the first carbon feels polar, just a little bit. And then the carbon here says, well, I'm not going to stand for that. And it tries to draw the electrons away from the hydrogens that it's bonded to. So there's a knock-on effect. The big bully, smaller bully, and the smallest bully, and it draws the electrons as they feel electron needy. So there's a bit of polarity to that bond, a carbon to hydrogen bond, when it's next to a carbonyl group, a carbon to oxygen double bond. And so the bond becoming polarized, it makes it easier for it to be broken. And so a molecule like water, which is only very mildly basic, I love using red for the actual arrows. So using a lone pair from the oxygen, says I'll have that, checks the hydrogen, and then the electrons in the bond, when that bond breaks, because of course hydrogen can only have a duet, those electrons retreat back to the more electronegative carbon. Usually when chemical bonds break, the more electronegative element will pick up the electrons. And so we produce these conjugate forms. First the ketone, minus that proton. A carbon with carbon anion character, with a charge on that carbon, and of course the water transformed into hydronium ions. Use a pair of its electrons to make that bond. So having given it control, we've got a formal charge on the oxygen. Having accepted full control of this bonding pair, which previously had been shared, of course, we get a negative charge on the carbon. You look at any reaction scheme, if there's no charge in one side of the reaction, we should have the same collective net zero charge on every other step as well. So there's our conjugate forms.
Is there a positive one charge on the oxygen?
Yeah. When you think about it, not an ion charge, it's just about the relative share of the electrons. From the periodic table, the oxygen is the sixth element in the row. So out of its octet, it should control 6 of the electrons around it. 6 from 8. And of course the other 2 it normally gets by bonding with other elements, which is why oxygen is normally divalent. But how much does it actually control? It certainly has an octet, 2, 4, 6, 8. The lone pair belongs to it. And then 1 electron from each of the bonds also belongs to the oxygen. And so it only comes up with 5 of the 6 that it was expecting. That gives it a formal +1 charge, specifically on the oxygen. So to work out the formal charge of the atoms, you can look at where the element is in the table, how many boxes do we count to reach it. That tells us how many electrons it's supposed to control out of its greater octet. And then you look at the reality of your Lewis structure, and that will show it. Same with the carbon on the conjugate here. This carbon is the 4th element in the 2nd row, lithium, beryllium, boron, carbon. So it should control 4 of its electrons. How many does it control? Well, of course, there's still 2 hydrogens attached. Draw them in properly. So it has the lone pair, 1, 2, and then 1 from each bond, 3, 4, 5 of the 8 electrons around it. So it's a little bit too much. And it's a formal charge of -1 this time. We can do this trick with any element. And so, for the conjugate produced, like the other examples from online, it is actually resonance stabilized. And we've said that we look for that hot spot, an atom which is formally charged, in this case the carbon. It's got too many electrons, and we'd like to offload some of that electron density, and it offloads it to its neighbour. Here, take a share of this. It says it can do that because there's an atomic orbital on this carbon, which is being used to make the pi bond with the oxygen. So as those electrons come in to that atomic orbital, something's got to give. So the electrons retreat back to the far end of that pi bond, and we can produce this resonance structure. So that formal charge now goes to the oxygen. Heavy burden of charge on the atom leads to instability. But the more friends the molecule has, or the more atoms in the molecule, that are capable of sharing that burden and creating an increasing number of resonance structures, eases that burden and makes the molecule more stable. Like the more friends you have when moving house to carry the load. So we're not saying that this is equilibrium with the two molecules rapidly moving back and forth. We're just saying that the true character of the molecule partially has character like this, where the carbon's electron enriched. It also partly has character like this, where maybe it's the oxygen which is electron enriched. So instead of electrons being localized between two atoms, they're delocalized over a much larger stretch of the molecule, because they're all sp or sp2 hybridized atoms. Any atom is sp3, that breaks the sequence. That puts a big stop sign in the way, because sp3 hybridization doesn't have atomic orbitals on the atom. So this is what we often just describe as a delocalized system of electrons. They move around a bigger area. So there are some chemical reactions we can point to where the carbon would instigate a new chemical bond. This picture shows that because it shows that it has the electrons to make a new bond. And there are some reactions where we could instigate a chemical reaction at this point in the molecule. And our resonance structure here shows why that could happen, because we see the oxygen here electron enriched. Okay. That's again an example of the Bronsted-Lowry theory. One chemical giving away a proton, acting as the acid. One chemical receiving a proton, acting as the base. They both have conjugate pairs. The conjugate pair of the acid is a chemical which can act as a base by picking up that proton back. And the conjugate pair of the base is also an acid in the reverse reaction. It's almost like a game of tennis, just using a proton, a hydrogen ion, just batting it back and forth between these two chemicals. And we think of that person as being a different chemical depending on whether he has the ball or he has passed the ball on, passed the proton on. Okay, so that's our first definition for acid-base chemistry on an organic level. But not all reactions can be described from the Bronsted-Lowry theory, because they don't always involve the exchange of a proton. That's the problem. Related to this idea is the Lewis model for an acid and base. Lewis tells us that an acid is an electron acceptor, and a base is an electron donator. You can rationalize this by just thinking about the examples we have for acid-base chemistry, even just, let me just go back a second. Oh, I knew I shouldn't have erased it. Now let me put this up here a second. Think about that one we just did. From Lewis's point of view, the very act of giving away that proton to the base, okay, so Bronsted-Lowry tells us it's giving away a proton. The very act of giving away the proton made it accept the electrons from the bond. So we can either think of the acid as a proton donator or an electron acceptor. Conversely, from the base's point of view, we called it base because it was picking up protons, but the very act of picking that proton up causes it to relinquish and give away its electrons. Because it's using those electrons to pick up the hydrogen, so it's giving up control of its electron share. So there are many examples that can be thought of as both an acid or base from the Bronsted-Lowry definition and the Lewis definition. But if there isn't a transfer of a proton, it's only going to be Lewis. All reactions can be thought of as a Lewis acid or base, but it doesn't always fit for the Bronsted-Lowry definition, because there might not be a proton being exchanged. So there'll be many examples we'll look at where it's both. And there'll be some examples where it's strictly just a Lewis acid-base reaction. And so the Lewis acid-base definition is stronger and more robust. Here's a couple of examples of classic, strong Lewis acid and bases. You don't have to memorize these. I would ask you a jerk question like that in an exam, just to list one, and use one of these in a reaction, and then you could see over the course of the reaction mechanism that it was working as an acid or base. So the common acids that we're seeing, like sulfuric acid, nitric acid, zinc chloride is another one, Lewis acid catalyst like aluminium chloride and iron chloride, also commonly used acetic acid, magnesium, lithium, other group 1 metals, a good example, because over the course of the reaction they can accept electrons, and they're therefore acting as a Lewis acid. Common examples of Lewis bases, alcohols are good examples, aldehydes, ketones, amines and sulfides. Yeah, and it just gives you an idea. We'll get familiar with these because we'll keep looking at examples over the semester which use these. Well, there you go. There's the tidied up version of it. So we thought of this as an acid from the Bronsted-Lowry definition because it's giving away its proton. We can also think of it as a Lewis acid because it's receiving those electrons. Think of it as a base from the Bronsted-Lowry definition because it's picking up a proton but also using up, giving away its electrons. So if it's a proton donator, it's an electron acceptor. If it's a proton acceptor, it's an electron donator. Even now, I just lock in my head the Bronsted-Lowry definition, then I know to think in reverse if I'm thinking about electrons for Lewis acids and bases. look at a couple of extra examples before we finish off the chapter. Yes, just two more. Good. Just about the right time for having a break. Excellent. Cool. Yeah. Do keep me posted if I'm rushing through points where there's blanks in the notes. I'm just too old, I can't remember where I put the blanks anymore. Usually Hannah keeps me back. She'll give me a sign like that. Seems kind of rude, to be honest, but fine. There's the rest of the softball team. Did you decide that was too terrible, chemistry instructor?
No, I mean, you may have some freshmen, do you not have any freshmen? You may, you don't know yet, probably.
Not seeing anybody from, not for 201, I thought the rest of the gang were coming back for 201,
No,
202.
no.
No,
Just me and Sydney were the ones taking those classes.
okay, said changed their mind.
Yeah. I guess, I don't know, I didn't know any of them were taking this class.
Oh, I thought they were all planning on taking 201. Was I too mean to her?
To Sydney? No, she's just going to SIU, she didn't come back.
Okay. So the giving away of the proton makes it an acid, but the acceptance of the electrons also makes it an acid from the Lewis field. Picking up a proton makes it a base from the Bronsted-Lowry theory. The giving away control of its electrons, because they're now going to be shared electrons in that oxygen to hydrogen bond, also makes it a Lewis base. Okay, safe to move. Right, let's try. Actually, let's leave it over the break. So we'll take a 10-minute break. We can get up, go to the bathroom, take a look at those two. And tell me for each of our reagents on the left-hand side each time, which of them are acids and bases? But are they specifically Bronsted-Lowry or Lewis acids and bases? Maybe they're both. Maybe they're just examples of Lewis acid and bases. We will take a break there and come back in 10 minutes. Boo! Ah, gotcha.